Okay, so let us now start solving the exercises. Let D be a Euclidean ring. If its field of quotients. Recall that every Euclidean ring by definition is an integral domain, so it will have a field of quotients. Prove the Gauss lemma for polynomials with coefficients from D factored as products of polynomials with coefficients from F. So the original Gauss lemma, where we have polynomials with integer coefficients and which are factored as polynomials, as products of polynomials with rational coefficients, now has to be proved in this general setup, where in place of the Euclidean ring of integers you have a general Euclidean ring, and in place of the field of quotients of integers, that is the rational numbers, you have the field of quotients of this Euclidean ring. And it turns out that if one goes through the proof of original Gauss lemma as well as its statement, everything will work in this general case also verbatim. You don't have to do anything new, you don't have to apply any new strategy or anything. It will just simply work smoothly without any new thing required. So the solution can be written like this. The Gauss lemma in this setting and the corresponding generalization of lemma 3-10-1, because that is also involved in Gauss lemma, and along with their proofs are verbatim repetitions of the original ones. And the solution is just like that. Then excuse me, exercise 2. If P is a prime number prove that the polynomial x to the power n minus p is irreducible over the rational numbers. Over the rationals. Now in this case you can apply the Eisenstein criterion directly. How? You need a prime that satisfies the hypothesis of the Eisenstein criterion. So that prime you can take to be p. Note that the coefficient of x to the power n is 1, so it's not divisible by p. In Eisenstein criterion also the highest coefficient is not divisible by p. The others are divisible by p. Here the only other coefficient is this constant term minus p, which is divisible by p, and the constant term is not divisible by p square. So all the hypotheses of the Eisenstein criterion are true. So directly that criterion says that this polynomial is irreducible over the field of rationals. So we will just simply write like this without being too specific. It's a consequence of theorem 3.10.2, that is the Eisenstein criterion. Then exercise 3. Prove that the polynomial one plus x square etc. to x to the power p minus 1, p a prime number, is irreducible over the field of rational numbers. And we have a hint also, and this is the hint. Herstein is asking us to consider this polynomial, which looks like the original one, but with x plus 1 in place of x square. This is much more complicated than the original one, but apparently this will help us prove that the original one is irreducible. And use the Eisenstein criterion. Easier said than done, because this polynomial in the present form, in this form, is not suitable for applying Eisenstein criterion, because you can see that we need coefficients of x, okay, to be able to apply Eisenstein criterion. So that means we need to expand these powers, and for that we need the binomial theorem, and there is a problem with that. Problem means we have binomial theorem, but it's not something we know already. It's a little different from the usual binomial theorem, not in its form but in its interpretation. We have x plus 1 whole to the power n is equal to the binomial theorem, the expansion for the binomial theorem. The form is same, but the meaning of this equation will be different. N choose I, x to the power I, where I varies from 0 to n, for every positive integer n. The question is, what is the meaning of this? Ordinarily, when we have the binomial theorem, the binomial expansion, then we write it like this, equal to that sum, where a and b are either real numbers or complex numbers, something like that. Here, however, x is not a number, but x can be treated as a polynomial. Now, in this setting also, is the binomial theorem true in the original form? The answer is yes, but we haven't proved it anywhere yet. And that's why this needs a proof, which however we are not going to carry out, because the proof, again, like the original binomial theorem, is by induction on n, and there is no difference at all. So we are just going to mention it. It can be proved by induction on n, and for this we are going to refer to exercise 714. This will come, we are still far away from the 7th chapter in analysis 1 by tau, but there we have this exercise where tau asks us to prove the binomial theorem. So when we prove that, when we solve this exercise, we will see the proof. In fact, the proof of the original binomial theorem is available in many places. Okay, you may have already come across this. So that's why I don't bother to prove it here. Note carefully, this is important, that now the above identity means this identity has to be interpreted in this ring. That is the only difference. Okay. Okay, so now you consider this product of x and this polynomial. x can be written as x plus 1 minus 1, and the other polynomial stays like this. Now this is a standard identity in algebra, that is elementary algebra, that this is equal to minus 1. Okay, now this is the point where we will need this expansion, and if we expand 1, the first term will be equal to 1 according to this term, and what we will be left with in that sum, every term will have x, so that sum is actually equal to this. Where now I varies from 1 to p. Originally I varies from 0 to p, but for I equal to 0, that term is equal to 1, which cancels out with minus 1. And from this, since every term has x, so you can take x common out. Note that all these calculations are happening in this ring. Okay, so you should not forget that. So this is p choose I times x to the power I hope it is visible, I equal to 1 to p. Okay. So this calculation is needed only for the purpose of simplifying this original polynomial that the hint asks us to consider. Note that we multiplied the original polynomial by x, and we obtained again a product where we have one factor as x and another factor as this polynomial. Okay. Now we have got an equation in Qx of this form: x times one polynomial is equal to x times another polynomial. Now since this polynomial ring is an integral domain, so it has no zero divisor, and x is also not equal to 0. So by the cancellation law that is available in any integral domain, fx must be equal to gx. So this polynomial that we want to consider turns out to be equal to this. Since is an integral domain and x is not equal to 0, we have this equal to summation p choose I x to the power I minus 1, where I varies from 1 to p. So this will be equal to, if we just simply write the terms out, what shall we get? If we put I equal to 1, we will get p and x to the power p minus 1. oh no, sorry, not x to the power p minus 1. I am putting I equal to 1, not p. So we will get just simply p. Then p choose 2 x plus p choose 3 x squared. Like this it will go, and the last term will be p choose p, so x to the power will it be okay to write one more term before that? Yes, p choose p minus 1 x to the power p minus 2. In this term, in place of I, we are taking p minus 1, so we have p minus 2 here, and the last term is x to the power p minus 1. Okay, now for I lying between 2 and p minus 1, we have p choose I. By definition, this is what? P factorial divided by p minus I factorial times I factorial. So this turns out to be p times p minus 1 times p minus 2. Like this you will go till p minus I plus 1 divided by I factorial. After that you will have p minus 1 factorial, which cancels out with this one. Okay, no, that's not how I should have written this, or we can continue with this also, and p does not divide I factorial for this variation of I. The reason is that if you expand I factorial, what is the highest value? P minus 1. Even if you expand p minus 1, what is p minus 1 factorial? The product of the first two p minus 1 integers, positive integers. None of them is divisible by p, simply because all of them are less than p. So because p is a prime number, if p divides I factorial, p has to divide at least one of the factors which p does not. So that's why p does not divide I factorial for this variation of I. And this we have this, and hence let me write here, I factorial has to divide p minus 1, p minus 2, etc. up to p minus I plus 1. What is this conclusion and why is it true? This conclusion is true because you see, since p is a prime number and p does not divide I factorial, so p and I factorial are relatively prime. So there is no common factor between p and I factorial. However, we already know from combinatorics that these numbers are actually positive integers. So that means I factorial has to divide this. However, I factorial and p are co-prime, so that means I factorial has to divide the rest of the product. So in fact, in brackets we should have written it here itself, but anyway, note that this is an integer and the greatest common divisor of p and I factorial is equal to 1. So what does this mean now? It means that this ratio, this quotient that we get by dividing this part except the p by I factorial is actually a positive integer. In other words, p divides this p choose I or pci, whatever you may want to call it, because this p choose I is p times an integer. Thus, p divides this binomial coefficient. So what does that mean? It means that p divides all these binomial coefficients, okay, and p automatically divides p because the first term is only p. So what do we have now? The original polynomial that we were considering, not that original one but this one, turns out to be a polynomial like this, where all the terms are divisible by p except the highest coefficient, and the last term is not divisible by p square. So now the polynomial is in a form where we can apply the Eisenstein criterion, and the hypothesis of the Eisenstein criterion are also true here for the prime p. Let's write the variation also. For all integers so by the Eisenstein criterion, this is irreducible over Q. But now how can we use its irreducibility to derive the irreducibility of our original polynomial? For that we have to do a little trick. Let fx belonging to we cannot write belonging to, not yet. Let fx be a integer monic polynomial and integer monic polynomial. Morning prayer has started. Okay, so fx is an integer monic polynomial that is reducible over Q. So this is something else we are doing now. Okay, this much we have done. Now we are considering something else. So we have considered an integer monic polynomial that is reducible over Q. Then fx is equal to gx times hx, where gx and hx are non-constant polynomials over Q. Reducibility of fx over Q just means this, that fx can be written as a product of two such polynomials over Q. Both of them are non-constant, that is, both of them have positive degrees. Okay. Then by the corollary to theorem (3-10-1), oh, here we are considering no, wait. If this is reducible over Q, then we have been able to write, let me just see, I think I have a confusion. Reducible over Q. Okay. No, okay, there is no problem. So by the corollary to theorem 3-10-1, fx can be written like this: lambda x mu x where lambda x and mu x are both integer monic polynomials. Okay, so the availability of this type of factorization for fx over Q has led us to this factorization, where the polynomials are now over the ring of integers and both of them are monic. And this is a consequence of the corollary to theorem 3-10-1. We have already seen this, where we, if you remember, we used the content of a polynomial to carry out the proof. Okay. Now, since lambda x and mu x are monic, so their highest coefficients of both of them are equal to 1, and that is why if you consider the polynomials lambda x plus 1 and mu x plus 1, then their degrees will not change. See, the thing is this: if you have a monic polynomial like this, say x to the power n plus a1 x to the power n minus 1 etc. plus an, suppose. Now in place of x, suppose you are writing x plus 1, then this new polynomial, this is after all a polynomial, this new polynomial, to know this polynomial truly, you have to do all the binomial expansions. Now when you do the binomial expansions, you can see that the highest term will be x to the power n. No other x to the power n will occur, and it will also have the highest coefficient equal to 1. In other words, the degree of this polynomial is n, the degree of this polynomial is also n. It does not change. So that's what we are now going to write. Note that degree of lambda x is equal to degree of this, and degree of mu x is equal to degree of this. Also fx plus 1 is equal to lambda x plus 1 times mu x plus 1. This is not very difficult to see why that is the case. Okay, so what do we have now? These polynomials, the way we obtain these polynomials from these polynomials in the original proof of corollary, the corollary to theorem 3.10.1, you know that their degrees actually do not change. So the fact that fx and gx and hx are both non-constant implies that lambda x and mu x are also both non-constant, and that in turn implies, because of this equality of degrees, that lambda x plus 1 and mu x plus 1 are also non-constant. Since gx and hx are non-constant, so are lambda x and mu x. See the proof. Of the corollary to theorem 3.10.1, and hence lambda x plus 1 and mu x plus 1 are also non-constant. This implies, I think I need some ink. Okay, so this implies, so now these are non-constant polynomials and fx has been written as a product of them. So fx plus 1 is irreducible over the field of rational numbers, because although these are integer polynomials, after all they are rational polynomials also. Oh sorry, I mean reducible. I think I said irreducible. This implies fx plus 1 is reducible over q. So that means if fx is an integer monic polynomial that is reducible over q, we have proved that fx plus 1 is also reducible over q. In other words, for an integer monic polynomial fx, if fx plus 1 is irreducible over q, then fx is also irreducible over q, which is just the contrapositive of the statement we now proved. Thus, irreducibility of this polynomial, which we have proved, implies that our original polynomial this over q, so that also has to be written, implies this is irreducible over q, and there the solution ends. Two more problems are there. Let me just finish. If m and n are relatively prime integers, and if x minus m divided by n divides this polynomial, where the a's means ai's, okay, these coefficients are integers. Prove that m divides a naught and n divides AR. There is a slight, I won't say it's a mistake, but it's just something that should be made clear in the exercise. See, it's given that m and n are relatively prime, that is, their greatest common divisor is 1, and these are integers, and here they have written m divided by n. Now it is understood that when n appears in the denominator, then it has to be non-zero. However, from this condition, it does not automatically imply that n is non-zero, because you can take n to be 0 and m to be 1. The GCD of 0 and 1 is also equal to 1. But let's just assume that n is non-zero since it appears in the denominator. Now the thing here is that this polynomial divides this polynomial, where the AI's are integers. Note that since this is a polynomial in general in this polynomial ring, so this division is happening here. That means when you write this polynomial as a product of this polynomial and another polynomial, that another polynomial must belong to QX. That's what we mean when we say that division is happening here in this system. Then we have to prove that m divides A naught and n divides AR. Okay, now in this solution we have to use, I don't know any other way, we have to use a result from chapter 5, which is not very difficult or involved result. However, it is a result that we are going to use prematurely without proving. Since this divides A naught plus A1x etc. plus AR x to the power r in QX in this polynomial ring, it follows from Lemma 392. Lemma 392 is the Euclidean algorithm in this Euclidean, in this polynomial ring, which says that if you divide a polynomial by a non-zero polynomial, then you get a quotient and a remainder. It's just that. And Lemma 531. So this is something that we are using prematurely. That from these two things, if you go to this lemma and combine these two results, you will see that this division is possible only when this m by n, if you replace x with m by n, then you are getting a rational number. That rational number must be equal to 0. In other words, m by n must be a root of this polynomial. This is a terminology we haven't defined yet, but I think you know about it. A root of a polynomial is a number with which if you replace x in the polynomial, then the result is 0. So these two results combined tell us that if we replace x with m by n, then we are going to get 0. That a naught plus a1 m divided by n etc. plus a r minus 1 m to the power r minus 1 divided by this plus ar, this is equal to 0. Okay, now that is, if we can simplify this by multiplying by n to the power r, we will get this n to the power, or let us write like this. Let's keep the coefficients first. A naught n to the power r plus a1 m n to the power r minus 1 etc. plus a r minus 1 n plus a r m to the power r. Since m and n are relatively prime, the last equation, we have to write equal to 0. This equation implies this divisibility relations. M divides a naught and n divides a r. Why? You look at this equation. In this equation now all the terms are integers. In all the terms except the last one we have n. So all of them are divisible by n, and the right hand side is 0, that is divisible by n. So that means ar times m to the power r should be divisible by n. However, n will not divide m to the power r. In fact, they are relatively prime. That's because m and n are relatively prime. So in this term is divisible by n, of course, but n and m to the power r have no common factor other than 1 and minus 1. So n has to divide ar. So that from that we are getting this. A similar argument with m in place of n will give you the fact that m divides a naught n to the power r, but m and n to the power r are relatively prime, so m has to divide a naught. So that's how we get the result. And lastly, there is this exercise five. If a is rational, and x minus a divides an integer monic polynomial, prove that a must be an integer. And this follows directly from the previous exercise. Do you see how? Since a is rational, a will be of the form m by n or some integers m and n, which you can choose to be relatively prime. You can always cancel the common factors and bring the quotient or bring the ratio in a form where the numerator and denominator are relatively prime. Now in that, the denominator, which is this n, has to divide the highest term of the polynomial which x minus a is dividing. Since that polynomial is monic, the highest term is 1, so n has to divide 1. So that means the denominator n itself is either minus 1 or plus 1. But then the original rational number a must be an integer. So we are just simply going to write the solution like this. From the previous exercise. So this ends this set of exercises and it ends this section also. So I end the video here. If you are new here, please consider subscribing to my channel, A Mathematical Room. So with that, I sign off. See you in the next video. This is me, Lucifer, from A Mathematical Room. Have a nice night.